In the last two videos, I've been talking about the roots of polynomial equations. And in this video, I'll be looking at something still in that line of talking about roots and zeros of polynomial equations. And that takes us to the Vietas formula. Okay, talking about the Vietas formula, in this section, we study how the coefficients of a polynomial relate to the sum and product of its roots. So the coefficients of a polynomial equation can have relationship with the sum and product of its roots. Sometimes all you just know are the sum and product of the roots of a particular polynomial, and then maybe you want to now use that to find other things, maybe to get the polynomial itself and all of that. Then we focus on focus first on quadratics, then see how the ideas extend to higher degrees. So let's go straight. Talking about Vieta for quadratics. Consider the quadratic equation ax squared plus bx plus c equals 0, where a is not equal to 0. Of course, if a is 0, the whole thing becomes linear. So the fact that a is not 0 is what keeps it quadratic. And with roots R1 and R2, whether real or complex. So the Vietas formula for a quadratic are given as we have the sum of roots. So since you know the roots to be R1 and R2, so the sum of R1 and R2 is equal to minus B over A, and the product of roots. I think I did something like this in the previous video. I've forgotten which one now. But here we are actually settling down to derive it and to see how it all comes about, right? So you have a quadratic equation and you have the roots, of course, two of the roots, two roots, because a quadratic equation is expected to have two solutions. So you have the two solutions. So if you sum these two solutions, they will be equal to the negative of b over a, and the product of the roots r1 times r2 will be c over a, like that. So if the quadratic is monomic means that a is equal to 1, that is the coefficient of x squared is 1, that is x squared plus bx plus c is 0, then we say that r1 plus r2 will just be minus b, this b here, and R1, R2 will just be C because A is simply 1. So that is the basic idea of the Vietas formula. So that's Vieta for quadratics right there. So let's look at the derivation. So talking about the derivation now, you see, if R1 and R2 are roots of AX squared plus BX plus C equals 0, then we can write that A into X minus R1 into X minus R2 is equal to 0. Okay, if that is the case, we can then expand this. We have a into x minus r1 into x minus r2. And then we try to expand this whole thing now. Then we see that we have x times x squared, x times r2. That's x times minus r2. That's minus r2 x. Then minus r1. Okay, I guess I need to take it to the worksheet now, so we can really drive that home. Okay. Yeah. So once you derive the Vietas formula, that's basically what this is about. So given that ax squared plus bx plus c equals 0, and the roots are r1 and r2. Now, this R1 and R2 are what some other people may know as alpha and beta. Like it can pick any two. So it can be in my undergraduate days, we used alpha and beta a lot for this. So given that ax squared plus bx plus c equals 0, and the roots are R1 and R2, so to derive the Vietas formula, what do we do? So we can say that, or let me say, we can write, since R1 and R2 are solutions, or if it is alpha and beta, you want to use anyone. So we can write that A into, X minus R1 into X minus R2 is equal to 0, okay? Because, I mean, if you equate this to 0 now, you get R1 and R2. So this is very correct. And this A is here because if you are considering a case that is not monic, I've forgotten that the word. I think it's monic. Monic, yeah, monic is the word, right? So now we can write this because we know for sure that R1 and R2 are the roots. So if you solve this, you get R1 and R2. But then that we are not really solving here now. What we want to do is to expand. Okay, so if you expand, we have A into x times x, x squared. X times minus R2, that's minus R2x. Then minus R1 times x, that's minus R1x. Then minus R1 times minus R2, that's plus R1, R2. Okay. In fact, we don't need this because it's everything can go on like this, and this is equal to 0. So now we have A into, we can have x squared minus. So we can put these two together. So you can have minus outside. So you have R2 plus R1 x, so I mean, if you expand, you have minus R2x minus R1x, then plus R1, R2, like this. So if you want to write that better, so you have into A into x squared minus R1 plus R2x plus R1, R2, okay, which is equal to 0. Now, the next thing we want to do now, having got this expanded form, so what we want to do next is we want to compare this with the original expression. So we want to compare this now with the original expression. So let's go for that. So now, this guy, so we can compare. So comparing, well, I think I can still go ahead and expand everything. So we have ax squared minus a into r1 plus r2x plus a r1 r2 equals 0. So this now want to compare compare with the original form, comparing with the original, which is ax squared plus bx plus c equals 0. So we want to compare with this. So what does that simply tell us? So you see that, you see now, this, we have ax squared, we have ax squared. Good. So then it means we can then compare this with this because they are the ones with x. So we can then, so okay, I already changed the marker. So comparing the two now, we don't have any ax squared cancels out ax squared. So for x now, for x, for the first part, we have minus a into r1 plus r2 equals bx. This bx right here. Okay. No, sorry, we don't need that x because we already said it's in B, just B. So in that case, now we can just say that R1 plus R2 is equal to minus B over A. That's if we divide both sides by minus A, that is. So R1 plus R2 is minus B over A. On the other hand, if we compare this and this, so we can see that, that's and that. So we have, for constants now, let's say for constants, so we have up there, AR1, R2 equals C. So we have AR1, R2 equals C. So that means that R1, R2 equals C over A. And then we have this, okay? So with those in place, we have derived what the Vietas formula is about as far as quadratics are concerned. So that's exactly what we have right here. So R1 plus R2 is minus B over A. Then R1, R2 is C over A, like that. Okay. So that we can then say this. So for example, one now. So basic use of Vieta. I know Americans will call this Vieta or something like this. Okay. So we have basic use of Vieta. Find R1 plus R2 and R1, R2 for 2x squared minus 5x plus 3 equals 0. Simple. All you just need is get the components. So A is 2, that's the coefficient of x squared. B is minus 5, that's the coefficient of x. C is 3, that's the constant. So for the sum of the, so to find the sum of the roots, just have R1 plus R2, which is minus B over A. That's minus, B is minus 5, A is 2. So that's minus cancels minus, that's plus. So it means that the sum of the roots of this expression is 5 over 2. And the product, you have R1, R2, that's C over A. So that's 3 over 2 simply, okay? So using Vieta this way. So if all you're interested in is the sum and product of the roots of a quadratic equation or any equation for that matter, so you're going to find out, all you just need is remember the Vieta's formula, and you don't have to solve the equation to even get the sum and the product of the roots. So that's one beautiful thing about the Vieta formula. Okay, so building equations from sum and product. So using sum and product, now you can actually build equations like that. So suppose a quadratic has roots R1 and R2 with sum S is R1 plus R2 and product P is R1 plus R1 R2. So for a monic quadratic, leading coefficient 1, Vieta's formula says that R1 plus R2 is S, that's minus coefficient of X, and R1 R2 is P, that's the constant term. So the quadratic equation is simply x squared minus sx plus p. So generally speaking, what we are saying is that so if I go to the worksheet, I can just simply say this. I can make this bold statement that given that R1 and R2, if you like alpha and beta, given that alpha and beta or R1 and R2 are the solutions of a quadratic equation, the equation, or if you like quadratic a polynomial, the equation can be given as x squared, okay, x squared minus R1 plus R2x plus R1 R2 equals 0. That's we can make that bold statement in that case. So once you just know the sum and product, then you can just say that minus R1 plus R2x plus R1 R2, and that is equal to 0. So that becomes something interesting to work with. So if you know R1 and R2, then you can form the original equation by just putting things together this way. Okay, so we have a general non-monic case. So if you have an A, here we looked at a case where it's just x squared, not ax squared. So for a general non-monic case now, if the quadratic is ax squared plus bx plus c equals 0, so with leading coefficients a not 0, then we say S is R1 plus R2, which is minus B over A, P R1 R2, which is C over A. So given AS and P, now we can then write that AX squared minus, okay, AX squared minus ASX plus AP is 0. So if I go back here now, I think did I write the equation properly? I think I did not. Okay, I didn't bother about that. Okay, so I can just finish that up and say that for a non-monic case, case, for a non-monic case. So here what we have is, given that R1 and R2 are the solutions of a quadratic equation, here it has to be x squared plus bx plus c equals 0. Okay, for a non-monic case, ax squared plus bx plus c equals 0. Then we can have ax squared minus a into R1 plus R2x plus a R1 R2 equals 0. So that's what happens for a non-monic case where the coefficient of x squared is not 1, it's something apart from 1. Okay, so example 2 now, from sum and products. So from sum and products, find the monic quadratic whose roots have sum 5 and product 6. So that's easy, just say using. So in essence, now we're saying that R1 plus R2 is 5, then R1 R2 is 6. So all you just need to do is x squared minus R1 R2, that's 5x plus 6, and that is equal to 0. And we just keep moving. So for non-numeric roots now, a quadratic has roots 2 and minus 3. Find its monic equation. So first of all, find the sum. Sum is s, which is 2 plus or minus 3, that's 2 plus minus 3, that's minus 1. That's 2 minus 3, in short, that's minus 1. Then p is 2 times minus 3, that's minus 6. So the monic quadratic is now x squared minus sx plus p equals x squared minus 1x minus 6. And that's simply x squared plus x minus 6, right? So if you actually solve this, you get 2 and minus 3 for sure. I mean, we can do a quick thing. Instead of solving, we can use graphical method. So x squared plus x minus 6, x squared plus x minus 6. So you can see the point where they call the graph, where they call the x-axis are the solution. So we have solution at minus 3 and 2. And that's exactly what this tells us, minus 3 and 2, like that. So just once you know the two roots, add them, multiply them, and then fix them up like that. X squared minus the sum times x plus the product equals 0. Then we have, for non-monic equations, so a quadratic has leading coefficient a equals to root is sum is 4, then product p is 3. Then the equation is 2x squared minus 2sx plus 2p, 2x, that will be 2x squared minus 8x plus 3 equals 0. So in this case now, just like what I did over here, so you just have to multiply each part by a, right? Everything multiplied by a like that. So I think it just goes. So if you are given a and you're given the sum and the product of the roots, then you have the general thing multiplied by that a. So let's talk about transformed roots now. So there's possibility of transforming roots as far as Vietas formula is concerned. So let a monic quadratic, that is x squared minus sx plus p be 0, have roots r1 and r2. So s is r1 plus r2 and p is r1 and r2. Often we need a new quadratic whose roots are formed by transforming r1 and r2. E.g., maybe you need r1 plus k, or you need 1 over r1 or minus r1, and so on and so forth. You can have such transformations. So we use the new sum and product to construct the new equation. So imagine we have roots r1 plus k and r2 plus k. So new roots will now be r1 plus k and r2 plus k. So in that case, now you need to find the sum and the product. So if you find the sum, you have r1 plus k into r2 plus k equals. So if you put all this together, that's r1 plus r2 plus k, that's 2k. So in short, this r1 plus r2 is sum plus 2k. And then the new product will be r1 plus k into r2 plus k. So if you multiply all that, r1 times r2 is r1 r2, r1k, that's r1k, r2k, that's k times r2. So you have k into r1 plus r2 plus k times k, that's k squared. So at the end of the day, you have r1 r2, that's p plus ks plus k squared. So the monic quadratic with roots r1 plus k and r2 plus k is x squared minus s plus 2k, right? Notice the sum now, s plus 2k x plus p plus ks plus k squared equals 0. So we can have that kind of transformation. So whatever the new root is, you just go ahead. But of course, based on the original r1 and r2 that you are given. So I'm sure we're going to see an example of this pretty soon. So what if you want the roots to be transformed to 1 over r1 and 1 over r2? That's like, if you use alpha beta, for those who use alpha beta, that's 1 over alpha and 1 over beta. Okay, so assume in this case now, of course, you have to assume that r1 and r2 is never 0, because if they are 0, these things will be undefined. So p, of course, will have to not be 0. So in that case, the new sum will be 1 over r1 plus 1 over r2. LCM is r1, r2. R1 in r1, r2, that's r1, plus r2 in r1, r2, that's r1. So it means you have sum over product here. Therefore, the product now, you have 1 over r1 times 1 over r2. That's simply 1 over r1, r2. That's 1 over p. So a monic quadratic with this root will simply be x squared minus s over p. You know, the sum now, s over px plus 1 over p, 0. So to avoid fractions, you can multiply through by p, so that you now have px squared minus sx plus 1 equals 0. Okay, so that's talking about transformations. So what if you have roots? You have roots. The new roots now, instead of just r1 and r2, they are minus r1 and minus r2. So the new sum will just be minus r1 plus or minus r2. That's minus r1 plus r2, and that's minus sum. Then for the product, you have minus and minus plus r1, r2, that's r1, r2. So the product remains the same, like you had r1, r2. So the monic quadratic would now be x squared minus sx plus the product p, which is x squared plus sx plus p, and that is equal to 0, just like that. Okay. Uh, if you have roots kr1 and kr2, as usual, just do the sum and the product, that's all, and form the new equation with those sums and products. So new sum, you have kr1 plus kr2, and that's simply k into r1 plus r2, that's k times s. Well, the new products, you have kr1, kr2, that's k squared r1, r2, that's k squared p. Then just have x squared minus the new sum times x plus the new product, and that is equal to 0. So what if you now want the roots? Okay, like we're talking about new roots here. I guess, what was it here? Okay, two of this. So here we have roots. Why is this looking like this? I don't want this. Oh, okay. I wasn't really dealing with that. Okay. So this is, aha, that's why it was small. Yeah, so what if you now have roots r1 squared and r2 squared? The process is the same. Find the new sum and the new product, and you're good to go. So the new sum is just r1 squared plus r2 squared. So that's r1 squared plus r2 squared is still is simply the same thing as r1 plus r2 all squared minus 2r1 r2. So r1 plus r2 is sum squared minus 2 times the product. And then the product, you have r1 r2 all squared, that's r1 r2 all squared, which is p squared. Then you form the new equation x squared minus the sum x squared minus 2p x plus the product p squared equals 0. So those are some possible transformations you can definitely have. Okay, so let's solve this now. Imagine you want to form a new equation. So the quadratic x squared minus 5x plus 6 is equal to 0. Has roots r1 and r2. Find the quadratic whose roots are 1 over r1 and 1 over r2. Okay, so of course you can say S, you sum up, you get 5, you add, you get 6, and then you now use that here. But let me go ahead and do all this in details since I've just been talking about these things. So x squared minus 5x plus 6 now. So do I remember that now? X squared minus 5x plus 6 is that? Yeah, minus 5x. And the roots are R1 and R2. Okay, okay. All right. Where am I? Okay. R1 and R2, right? R1 and R2. Okay. Given that the roots of x squared minus 5x plus 6 is equals 0 are R1 equals to that. Okay. And when we solve this, we get minus 2 and minus 3. No, we get 2 and 3. So yeah, we get 2 and 3. So R1 equals to, and R2 equals 3. Okay. Find a new quadratic and a new quadratic whose roots are 1 over R1 and 1 over R2. I hope that is correct. Is that correct? I think it is. Yeah, this is where we are at. So yeah, these are the new roots now. Okay, so this is what we have to do. So here, first of all, we need to know that so for the solution, we need first of all that R1 is 2 and R2 is 3. So we know that R1 plus R2 is equal to 3. I mean, is equal to 2 plus 3, and that is 5. First of all, settled. Then we have R1, R2, that is 2 times 3, that is 6. So also settled. So we now say for the new roots now, for 1 over R1 and 1 over R2. So we have new sum, new sum. Well, we need product and sum always. New sum will be 1 over R1 plus 1 over R2. So the LCM is R1, R2. So R1 in R1, R2, that's R2 plus R2 in R1, R2, that's R1. So in short, we have R2, R1 plus R2. I mean, just for sake of neatness or something. So R1, R2. So the new sum is R1 plus R2 over R1, R2. So we know R1 plus R2 is 5. R1, R2 is 6. So we just have 5 over 6. So new sum is 5 over 6. We keep that. Then we go for new product too. So new product, okay, is such that we have R1 times R2. So that's simply R1, R2. And that is simply the same. Oh, sorry. That's my bad. So the new product will be 1 over R1, rather, 1 over R1 times 1 over R2. Okay, and that is equal to 1 over R1, R2. So R1, R2 is already known to be 6. So we have the new product to be 1 over 6. New product is 1 over 6. So what do? We say, so, okay, I want to change this. So the new quadratic is x squared. All right. I mean, this is monic. It's monic because the coefficient of x squared is 1. So if it wasn't monic, we have to multiply through by that coefficient. So the new quadratic is x squared minus the sum now, the new sum, as new sum multiplied by x plus the new product, okay, plus the new product, and that is equal to 0. So what that means is that we have x squared minus the new sum, like we got, is 5 over 6. So we have 5 over 6x plus the new product is 1 over 6, and that is equal to 0. To make things tidy, we can multiply through by 6. So if we multiply through by 6, we have 6x squared minus 5x plus 1 equals 0. So this is the new quadratic whose roots are 1 over R1 and 1 over R2 easily. Okay, so that's why we have this right here. Then we have inequalities using sum and product. That's another heading altogether. So let's see this. So for inequalities using sum and product, let ax squared plus bx plus c be equal to 0, and a is not 0. Of course, you know why? If a is 0, of course, it becomes linear, like I keep saying. So they have roots R1 and R2, and they are assumed to be real. Then we say that R1 plus R2 is minus b over a, and R1, R2 is c over a. We established that already. To discuss signs of the roots, we can combine the sign of R1 plus R2, which is sum, the sign of R1 and R2 for product, and then the condition for real roots, that's discriminant, right? So, and we say that the discriminant is b squared minus 4ac greater than or equal to 0 because we have assumed they are real. So for simplicity, we assume that a is simply greater than, this a now is greater than 0, just to simplify. Okay, so that means a is positive. If a was negative, maybe it would be something else. So if you now have, if both roots are positive, that is, if R1 and R2 are both positive, then the sum will be R1 plus R2 greater than 0. And then the products will be R1, R2 also greater than 0. So in terms of coefficients with a greater than 0, then we say that R1 plus R2 is equal to minus b over a, and minus b over a will be greater than 0, right? Which implies that minus b has got to be greater than 0. That implies that b is less than 0 in that case, okay? So in that case also, R1, R2 is equal to c over a greater than 0. That means since we already established that a is greater than 0, then c automatically is also greater than 0, okay? So if we need real roots now, so the discriminant is now such that b squared minus 4ac is greater than or equal to 0. So for a greater than 0, both roots, if both roots will be positive, the discriminant will be greater than or equal to 0, b will be less than 0, and c will be less than 0. So if you have both roots to be positive. So for both roots negative, the approach is a bit different. So what we have here is this. If R1 is less than 0 and R2 is less than 0, then the sum R1 plus R2 will automatically be less than 0. Okay? And R1 times R2 will be greater than 0 because these two are negative now, so automatically their sum will be negative, but their product will be positive. So for A greater than 0, in that case, R1 plus R2 is equal to minus B over A less than 0, which implies that minus B is less than 0, and that implies that B itself is greater than 0. If you divide through by minus, so, the inequality changes, then R1 and R2 is greater than 0, and since A is already greater than 0, then C itself is greater than 0. So, and we have that the discriminant is greater than or equal to 0. So for A greater than 0, both roots are negative. If the discriminant is greater than or equal to 0, all right, and B is greater than 0 as well as C is greater than 0. Okay? So what about we talk about the roots of opposite signs? If one root is positive and the other is negative, then the product, one is positive, one is negative. So we have R1, R2 less than 0 for the product straight up because the signs are different. So this is going to be R1, R2 is negative. So for A greater than 0, then we say that R1, R2 is equal to C over A less than 0. And that implies that C is less than 0. And in this case, we don't worry about the sum because, I mean, the sum it can go either way depending on which is bigger between R1 and R2. And then the discriminant is greater than or equal to 0 for real roots. So the roots have opposite signs. If the discriminant is greater than or equal to 0, C is less than 0. And as far as it is guaranteed that A is greater than 0, and we don't bother about B. So talking about parameter inequality now, example 6, find the range of k such that both roots of x squared minus k plus 3x plus 2k is equal to 0 are positive. So you want to guarantee that they are positive. So here we know that A is 1, B is minus k plus 3, that's the coefficient of x, and C is 2k. So for A, which is equal to 1, that is already greater than 0. And then for both positive roots, remember the conditions. The discriminant has to be greater than or equal to 0, B has to be less than 0, and C has to be greater than 0. So for condition that B is less than 0 now, so we take the B, that's minus k plus 3 less than 0. So if you divide through by minus, that means that k plus 3 is greater than 0, which implies that k is greater than minus 3. So k has to be greater than minus 3 here. Then for condition C, which is greater than 0, so we have 2k greater than 0. That implies that k has to be greater than 0. And for the other condition, so for the condition that the discriminant has to be greater than or equal to 0, that means that b squared minus 4ac will have to be, so b squared is, when you square this, the minus disappears. So we have k plus 3 squared minus 4 times 1 times 2k, that's 8k. So it has to be greater than 0. So we have greater than or equal to 0. So if you expand this now, we have k plus 3 all squared. So from what we learned about that square trinomial thing, so what did we call that? Trinomial I think it's square trinomial, yeah? So we expand, we have k squared plus 2 times k times 3, that's 6k plus 9, then minus 8k. So 6k minus 8k, that's minus 2k. So k squared minus 2k plus 9. So the discriminant of k squared minus 2k plus 9 is, so for the discriminant here now is now minus 2 squared minus 4ac, right? And that is 4 minus 36, and that is minus 32, which is less than 0. So k squared minus 2k plus 9 is always positive. Thus, the discriminant, the discriminant is always greater than or equal to 0 for all real value of k. So combining all conditions, the strongest condition is that k has got to be greater than 0. So both roots are positive when k is 0. Okay, that might feel like something way above your head, but not to worry. So you just want to go over that again. So extension of Vieta to higher degrees. So we have been using Vieta rule for quadratics, and we went all the way. So you should also understand that for cubic, quartic, or any kind of expressions you have, the Vieta's rule can apply. Vieta's formula can definitely apply. So Vieta's formulas extend to any polynomial. So consider a cubic, like ax cubed plus bx squared plus cx plus d equals 0. Of course, a must not be 0. If a is 0, then it's no longer cubic. So it should be guaranteed not to be 0. So we choose R1, R2, and R3. Then sum of roots will be R1 plus R2 plus R3 equals the coefficient of x2, and that's minus b over a. We have that. Then apart from that, in addition to what we have always done, then we're now going to have sum of pairwise products. So we have R1, R2 plus R2, R3 plus R3, R1, and that will have to be C over A. So it keeps going like that. So minus B over A, C over A. And lastly, for product of roots, we have R1, R2, R3 equals minus D over A. So you see the signs are changing. So minus B over A, C over A, then minus D over A. So it means that if you are going for fourth order now, so it means that R1 plus R2 plus R2 plus R4 will simply just be minus B over A again, because B will be the coefficient of x cubed in that case. So that's what we have here. So in this case, these are called the elementary symmetric sums of the roots. So these are called the elementary symmetric sums of the roots. So it means you can actually generalize it for n, for a polynomial of degree n, basically. So we have a nice example here. Cubic Vieta. So if x cubed minus 6x plus 11x minus 6 is equal to 0, so has root R1, R2, R1, R3, then we can say that R1 plus R2 plus R3 will simply be equal to minus B over A. That's minus 6 over 1. That'll be minus 6 over 1. And then the answer is 6 here. Then for R1, R2 plus R2, R3 plus R3, R1 will just be 11. And then the next one now, you have R1, R2, R3 equals minus D over A. So that's minus 6, minus 6, right, over 1. And that is going to be 6 again. So indeed, we have that. So we have that x squared minus 6x squared plus 11x minus 6. If you factorize, you get x equals x minus 1, x minus 2, x minus 3. So that means the roots are 1, 2, 3. So if you put them together, so 1 plus 2 plus 3 is 6. Then here, 1 times 2, 2. This is 2 times 3, 6. So that's 2 plus 6, 8, right? Then this one, 3 times 1, 3. 8 plus 3 is 11. And then you have 1 times 2 times 3, that's simply 6. So that actually works. So the Vietas formula holds for any kind of polynomial. So you want to relax and break it down and see how that goes. So we can actually generalize the Vietas the general pattern for degree n, which is informal now for Vieta. So we can just say for an x raised power n plus an minus 1 x raised power n minus 1 plus all of that up to ax a1x plus a naught equals 0. So we treat r1, r2 up to rn. The coefficients encode, number 1, you have minus sum of all roots in the coefficient of x raised power n. That means that we have r1 plus r2 plus r3 up to rn is equal to minus an minus 1 all over an. That's what that is about. Then the next thing that we have R1, R2, R2, R3, R3, R4, R4, R5, up to Rn like that. And then that will be positive of whatever is next. That's an minus 2, all over an, right? And we go on like that up to the product. So where you have R1, R2, R3, R4, R1 times R2 times R3 times R4 up to R times Rn. That would now be plus or minus, depending on the number of terms you have. So that's some kind of generalization. So this allows us to solve simple symmetric problems about roots without finding exact roots explicitly. So this is, the Vietas formula is simply telling us that we don't need to know the exact roots of an expression to be able to do some other things about it, to know the sum of its roots. You don't need to know the roots to know their sum and to know their product. Basically, that's what Vietas rule is teaching us, okay? So we have some practice questions here. For x squared minus 7x plus 10 equals 0, find R1 plus R2 and R1 plus R1, R2 without solving the equation. Okay, I think I want to do this. X squared minus 7x plus 10. Okay, x squared minus 7x plus 10. So find the sum and products of the roots of x squared minus 7x plus 10 equals 0. Simply. So what I'll just go ahead and say, suppose the roots, it doesn't have to be R1 and R2. Suppose the roots are alpha and beta. What do? The sum of their roots. So alpha plus beta, we already know that to be always minus b over a. Okay, and alpha beta, we know that to be c to be C over A. C over A. So what do? All you just need to do is identify the components. So we say from x squared minus 7x plus 10 equals 0. We know that A is equal to 1, B is equal to minus 7, and C is equal to 10. So alpha plus beta is simply minus B over A, which is minus 7 over 1, which is simply 7. That's the sum of the roots. Then alpha beta, which is the product of the roots, will now be C over A. C is 10. A is 1. That's simply 10. Okay? So with this now, you just know that. Therefore, the sum and products, of the roots of x squared minus 7x plus 10 equals 0 are 7 and 10 respectively. So how are you sure this is correct? You can check. So we can do a quick check. Okay. So you have x squared minus 7x plus 10. So to check, you can easily factorize this. So we need two numbers to multiply to get minus 7. Okay. So I know 5 times 2 will give us 10 because minus 7 is in the center, so the two of them have to be negative. So it means that this is simply x minus 2, x minus 5 equals 0. That's correct. If you expand x times x squared minus 2x minus 5x, that's minus 7x, then plus 10. So you have, it means that alpha is 2 and beta is 5. So you can see that alpha plus beta really is 7, and then alpha beta really is 10. That's how you go about that. Okay. So I think, so you can try other questions. So construct the second one from 3x squared plus 4x minus 2 equals 0. Compute R1 plus R2. So easily, so that's minus B over A. That's simply minus 4 over 3 for the first one. And then that's R1 over R2, that's C over A, that's minus 2 over 3, and so on. So for 3, construct the monic quadratic whose roots have this. So for this one, I just know it's x squared minus 7x plus 10, basically. And here you have x squared plus 4x, because that'll be x squared minus 4x plus minus 5. That's x squared plus 4x minus 5, basically. Then find the quadratic with leading coefficients 3, whose roots have s equals to p minus 4. So the only thing is you do the regular thing, then you now multiply through by 2. So first of all, you have like x squared minus 2x minus 4. So multiply by 2. Now that's 3x squared minus, that's 3x squared minus 6x minus 12 equals 0. That's how that goes. So this question 5, question 6, question 7, question 8, 9. Oh, this one is up to 13. So these are the questions 8 to 13. You have them here. So this is where transformation of roots and all those inequalities, you can also try this out. Yeah, I want to stop here. Thank you so much for listening. Let me know how helpful this is for you. And if there's something else you'd like me to do, feel free to let me know about it. I might just be able to pull that off. If you have subscribed already, I thank you so much for subscribing. If you haven't subscribed, of course, you don't want to keep missing out on anything on this channel, why not go ahead and subscribe right now, hit the notification bell so you can always get alerted each time a new video is released. Having done that, you may also want to become a member of the channel by clicking on join. That gives you 3 levels of access as a member, and with some special privileges attached. So you want to definitely avail yourself of all of that. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.